That one's working. And we are just about to kick off Facebook, and we have 9 people so far.
Hey. Hello, Gavin. Hello, George. Hello, Sarah. Hello, Gavin.
There we go. Right. So with that, I will take us off there. And good evening, everyone. We've got most of you here, which is always a good sign. I don't like it when people go missing. So you're all okay, and I'm glad to hear it. And welcome to our regular, I think I can now say it's regular, Thursday night Cafe Sci with Chris Bohr talking about microwaves, mobiles and masts. So bit of an introduction, then I'll run through how it works, and then we'll get started. First of all, this is a Cafe Sci. We've run it in a wine bar, an art gallery. They're running coffee shops, bars. There's a few in lecture theatres, but we're fairly convinced they're doing it wrong if you've not got coffee, a bar or tea in hand. So grab a drink, non-alcoholic drinks are fine, and settle back and relax. The format of these is that we have volunteer speakers who are talking about a particular subject of interest to them, and usually that they've done some research on. Our definition of science is quite broad, but anything where someone has looked into it, done some sort of testing, looked at the evidence, and has something interesting to say about it that they care about counts as science for the purposes of our Cafe Sci. In this particular case, Chris Bohr is I think expert is fair to say in microwave scanning and general scanning of the human body, as well as electromagnetic radiation, and particularly in a medical context. And he'll be talking about how it interacts with the human body, how it's used in cancer screening, and some other interesting areas. He is my dad, full disclosure. I am slightly biased there, and I have to admit that now, but he is also a doctor of physics. He's been working in signal processing and working with electromagnetic radiation for years, so he does know what he's talking about, although I wouldn't necessarily trust him on telecoms, but he is fine on microwave radiation. So with that, Chris.
Hello, thank you very much. Yeah, pleased to be here. It's really nice that the Cafe Sci is online now, and I have got a glass of wine. As we say, it doesn't have to be an alcoholic drink, but it can be a drink of some kind. I became interested. I'm not sure you would say I was interested. I started to get involved in microwaves during my undergraduate degree, and it came about, as so often happens with me, by being inspired by a particular person who made a single remark. John Blakey, who became a friend very late in life before he died, was a lecturer in electrical engineering. And one day we were in the practical labs, electrical engineering labs, and John Blakey came in and said to me, he said, Chris, he said, all you do is you twiddle all the knobs and see what happened, which has absolutely got me bang to rights. But as with so many of these things, from that day onwards, I didn't just twiddle all the knobs to see what happens. Well, I did, but I wrote down what I was doing and why I was doing it and continued twiddling the knobs, but with more of a sort of logical, informed thing to it. And I did a 4-year degree. My 3rd year was an industrial year. And because I was absolutely rubbish at electrical engineering, some awful thing in me made me volunteer to go and work at GEC in microwave engineering, which was actually the beginnings of what was called System X. That was digital telecoms. They were the first digital telephone exchanges. And my job was to scrape a little bit of gold off a track and then measure its reflection coefficient, plot it, go and write out a load of punch cards, take them to the punch card operator and go back the next day to find the bugs that I hadn't found in the punch card program. My PhD took me into it much more and into interaction with the human body, because I studied MRI. In those days, it was called nuclear magnetic resonance, but we dropped the nuclear because people got dead scared of it. And so now we call it magnetic resonance imaging. And that's really an interaction of radio and magnets with the human body. So I thought I'd try to take you through a sort of perambulation. First of all, to talk a little bit about what microwaves are, and I'm not sure that we really know because they're kind of strange things, really. How we use them in mobile phones and microwave ovens specifically, what they do, how they heat us up, how they affect the mobile phone, and then because of the 5G interest, shall I say, I'll talk a bit about how they affect our health and the mechanisms by which they might affect our health that could conceivably lie at the root of some of the, I won't call them conspiracy theories, but some of the concerns that people have about it. And while I do that, I'm going to be doing some simple experiments that you can do at home. So like Blue Peter, I've got ones that I've made beforehand, but I'll explain to you a little bit about how you can do it yourself. So James, can you switch to my phone camera, please?
Yep, and just while I'm doing that, for those who haven't been to one of these events before, I realised I left something out. If you'd like to interrupt or ask a question or would like me to interrupt on your behalf, if you either click the raise hand button or just type a question in question and answer, I will rudely interrupt Chris and challenge him with the question. I may wait until after he's mid-sentence, but it will be asked and you should get an answer. Okay.
Okay, I think the phone might be at right angles for the moment for you, so I'll have to swap myself around a little bit. So microwaves, what actually are they? Well, they're a form of electromagnetic radiation, and electromagnetism is really interesting because it's something that propagates through empty space. This is a magnet, and a moving magnet generates an electric field. A moving magnet causes electricity to move in its turn. And so here what I've got is I've got a coil. Now I made this just by taking some mains wire, splitting it down the middle, taking out the blue wire, and then I just coiled it around this plastic tube. It makes an electromagnet, but it also makes the core of a dynamo. It's not a very good electromagnet because the coils aren't close enough. If you want to make an electromagnet, you need to go around many, many more times, but I really lost the will to live. This is a voltmeter, and hopefully you can see here it's reading. So all I'm going to do is just demonstrate that a moving magnet generates an electric field, because I'm going to drop this magnet through here and watch the voltmeter quite closely because it's quite quick. So moving magnet creates an electric field. Did you see that? Okay. Also, an electric field moves a magnet. So these are like to and fro's here, and it's quite interesting, I think. This is not a very good electromagnet, but it's enough to move a compass needle. So can you see the compass needle on here? What I'm going to do is I'm going to connect up this battery. It's actually a 9-volt battery zapping through here, so it's not very effective. And watch the needle. It moves. Not a lot, but a bit. Yeah. That's because it's not actually a very good electromagnet, but it's enough just to demonstrate it. So we've got two things that are happening here. First of all, a moving magnet is creating electricity. And secondly, moving electricity is creating magnetism. And these come out to what are called Maxwell's equations. Maxwell's equations strike fear into generations of electrical engineers. They're considered to be some of the most fiendish equations known to man, and they're actually extraordinarily simple as equations. The reason that people get terrified by them is that their solutions are difficult, or shall I say impossible, except in three simple cases. The equations are this. This is grad dot E. E is the electric field here. Yeah. This is grad cross B. Well, grad is just an operator that says it's the gradient. So all this says is there's a slope in the electric field, which is proportional to the electric charge. So the electric field is created by the electric charge and drops off as the electric charge. Oh, Sarah tells me this is upside down. Is it? That's quite funny. Sorry. Thank you. Well, they make as much sense to me upside down as they do the way up. These two are the key, though. And this is interesting because I gave a talk to a class of 10-year-olds on waves, and I mentioned Maxwell's equations and introduced them to them because I thought it's good for 10-year-olds to see things that are so complicated they might not comprehend them. This operator here, grad cross B, says it's called a curl. What it means is that something curls around something else. Here the B is a magnetic field and the E is an electric field. And what this says is that an electric field causes a magnetic field that curls around it. And this one here says that a magnetic field causes an electric field that curls around it. Now, you need to think about this just very briefly, but it's actually quite simple. So I create a moving electric field. That electric field creates a magnetic field. That magnetic field creates an electric field which opposes the electric field that I first created. Yeah. So I create an electric field that causes a magnetic field that cancels the electric field, that then creates a magnetic field that creates the electric field that creates the magnetic field that creates the. These go in a circle like this. And amazingly, a 10-year-old girl came up to me after that talk and said, "So I just want to make sure I've written this down correctly. Do you mean that this pushes it this way, and that pushes it that way, and that pushes it this way, so it all goes around in a circle?" And I said, yes. And I thought that was one of the most amazing things I've ever heard, because I've had undergraduates actually weep about these things. We know something that does something similar to this. And it's not a very good analogy, but it's enough to, well, it's fun. Right? This is a gyroscope. A gyroscope has angular momentum. Angular momentum goes along this axis here as the gyroscope spins. And if I hold it here, then the gyroscope will try to drop down like this. But the dropping down like this with angular momentum, goodness knows why, I never really understood it, causes it to move in this direction. So we try to move in this direction, but it moves it in this direction, and you'll see what happens. You all probably had these things as toys when you were a child. So I hold it like this, and the gyroscope rotates, and that's what the magnetic field does. So the electromagnetic field is something that causes a rotation, and that's caused a wave. And that's why these diagrams here show this helix, because as time goes on, my magnetic field winds its way through space. That's the curl. So it's a gyroscope and it generates waves. Well, those waves propagate on their own. It's kind of magic. They don't wave anything, they just go on. You can see them in water sometimes. They're called solitons, and a soliton is a water wave that keeps itself going. If you look at meteorological maps and look them up, soliton, S-O-L-I-T-O-N, you can sometimes see the radar detecting a wave that's created as the water goes in through the Pillars of Hercules, and that wave or little wave group propagates all the way through the Mediterranean without ever dispersing, without ever dying down. It's just a thing. And that's like, if you like, the electromagnetic photon. So here we come to acknowledge how we use them to transmit signals. David Hilbert was a German mathematician who thought all mathematics should be proven from first principles. So you weren't allowed to start with an advanced theory and move on from that. You had to go right back to the very principles of mathematics. And Kurt Gödel, who some of you have probably heard of, proved him wrong. Gödel was a PhD student, and he came up with a very simple and elegant proof that showed that mathematics cannot prove itself. Indeed, no logical system that is sufficiently sophisticated to contain simple arithmetic can prove itself without bringing in something from the outside world. Now, that was the collapse of the Hilbert School of Mathematics, which was about 30 years worth of work for mathematicians, and we all feel sorry for them. But Gödel's method was quite productive. In the beginning, what he did was he said, we can take all the statements that anybody could make, and we can allocate a number to them. And that's how he showed that you can't prove everything through mathematics. But you can allocate a number to any statement. So you can allocate a number to any message. Anything I say can be allocated a single number. So here is the basis of coding. So in this case, I've got an alphanumeric code here, where each code is allocated a number. So A is 65, B is 66, and so on. So for example, cat would be C, 67, A, 65, T, 84. So cat would be 67, 65, 84. And that's a code that I can now send as a numeric code. Signals, for example, 83, 73, 71, 78, 65, 76, 83. Now, those numbers I can represent as levels here. So those could be the levels of a wave, and that's the modulation of a wave. So I can send a message by encoding it in as a string of numbers, and all I need is the key to the code, which is this here. Yeah. Now, we can actually do this in various ways, because our keying allows us to specify that we modify the size of the wave, or we can modify the frequency of the wave, that's how rapidly it varies, or we can modify the phase, that's where the wave's peak sits along the time axis. So amplitude modulation is AM, that's AM radio. Frequency modulation is FM, that's FM radio. Phase shift keying is PSK, that's what I worked on in System X, and that's modifying the phase of the wave. So if you're listening to AM radio, you're listening to an encoded waveform. If you're listening to FM, you're listening to it encoded by varying the frequency, and you don't listen to PSK. Well, you do on your mobile phone, because your mobile phone uses all three of those. We modify the amplitude and the frequency and the phase in order to encode. So we've got 3 bites of the cherry, and that's what allows us to send so much information as we go. Now, the range of a microwave is dependent on its frequency, or more properly, its wavelength. The length of the wave determines how far it travels. The longer the wave, the further it can travel. And it's attenuated, that is, it's absorbed by dust and moisture and things like that in the atmosphere. And that's why if there's a fog or something like that, maybe your mobile phone signal is not as good as it should be. The unfortunate thing is that the longer the wavelength, the less information you can encode. It takes a long time to modify a long wavelength signal. So to transmit more data, you need a higher frequency or shorter wavelength, and the shorter wavelengths have less range, which means you need more mobile phone masts. And that's how we get into the proliferation of mobile phone masts with the 5G, because our 3G and 4G signals go up to about 5 gigahertz, that's 5,000 million cycles per second, whereas 5G goes up to something like 60 gigahertz, that's 60,000 million cycles per second, and therefore they have a shorter range, and that's why you need to have mobile phone masts on lampposts and in your actual neighborhood. Yeah, okay. I just want to show you some of the things we can do with these. So first of all, before I go into some of the applications in terms of actual imaging, I want to show you why mobile or Wi-Fi signals interact with us. What's the first application of microwave radiation? Well, it was radar, actually. So radar was used with microwave radiation, that's very shortwave radiation, to reflect off enemy aircraft and detect where they were, so you can see them. And I knew radar operators because I was an instructor officer for the Navy in one life, just occasionally. And I talked to them about the possible harmful effects of microwaves, and they said, oh, you know, we used to stand in front of the radars to warm our tummy in cold weather. I don't know if those people are still alive or not, but if they are, they were incredibly reckless individuals and shouldn't have been allowed to influence other people. Now, what I'm going to do here is, why does it influence, why does it affect our bodies? Why does it warm us up? Why does it cook meat? Well, first of all, we need to understand that electricity is like a glue. Now, you've all done this. Here is a plastic biro, and here is a bit of fleecy. I'm going to rub the fleecy here. What I do is, by rubbing the fleecy, I knock some electricity off it. I gather some electrons onto this pen here, and here I've got a little piece of tissue paper. We should see, provided it's not too damp, that we pick up the tissue paper. So electricity is a kind of glue. It sticks things together and it makes things sticky. And water is inside our bodies and is inside meat, and it's the main component of us. People sometimes say we're 70 or 80% water, and that's about right. So water is wet. That means it's sticky. It sticks to things. When it wets them, it spreads out and actually sticks to the surface. So I could put some water somewhere and then tilt the surface, and the water would form a drop and run quite slowly. It wouldn't just skid down it. And water is sticky because it's got peculiar properties. Water is H2, 2 hydrogens, and O, 1 oxygen. And the curious thing about oxygen is that it could attach 4 different atoms to itself. It's got 4 places where we could attach these hydrogens. These holes here indicate places where it could attach. And if you try to make a shape with 4 arms, and those arms are as far away from each other as possible, it doesn't make a cross like that because that's flat. It makes something called a tetrahedron, which has arms out here and here. And the tetrahedron has a 120-degree angle here between the 2 hydrogens. So these things are bonded together.
One second.
Yeah.
Just a quick question. If the wavelength of microwaves in a microwave oven is about 14 centimeters, why do the holes in the door need to be so small?
Well, strictly speaking, the holes in the door don't need to be so small. They need to be very small compared to the overall wavelength. But the holes in the door are the holes in the door are not forming what's called a Faraday shield. They're forming a partial Faraday shield. And so in principle, you should be able to get away with a mesh, but there's a degree of overkill. And also, as I'll show you later with the tinfoil, the effect isn't perfect. So the best way of shielding the microwaves, that's what the question is about, is to have a sheet of metal, of conductor, in front of the microwave. But our wavelength, the waves sort of squeeze through and spread out, and I'll show you that in a little while when I do the waves. So if you wait, I'll address that question in a minute. So these water molecules, they're what's called polarized. So what happens is these are neutral, and electrons are sucked, if you like, from the hydrogen to the oxygen, which means there's a charge at each end of this. So it's actually what's called a dipole. So we have a positive charge here because some electrons have gone, and a negative charge at this end. And that means that this can be rotated by an electric field. So if we have our electric field rotating, it can rotate this water molecule. And that's how the water molecule rotation occurs. So the water molecule is extraordinarily small, but it can move very fast. Typically, a water molecule is moving at about the speed of sound in water, which is 1,500 meters per second. And if you calculate that out, you find that because the water molecule is about 1/10 of 1,000 millionth of a meter long, the water molecule can rotate at about 2,000 million times per second. It's between about 2,000 million and 6,000 million times per second. So my rotating electric field can rotate this water molecule here. And what it does, it rotates it by 180 degrees, and then it goes back again. So instead of rotating it all the way around, it usually rotates it and then goes back and forth like this. But the water molecules are not just rotating in isolation. So if they were just rotating in isolation, that would have no effect whatsoever. It wouldn't warm anything up. The water molecules also have what are called hydrogen bonds that attach here to the empty spaces on the oxygen. And that's because hydrogens are, if you like, rather flighty. So this hydrogen here is attached to this oxygen, but it doesn't actually mind having a flirtation with another oxygen like this. And what this does is it builds up a long-range structure within the water, so that our water is a very peculiar substance and develops a shape that extends over an incredibly long range. That can be up to a millimeter or so. Some people suggest that almost all the water in the human body that's not just bulk water is actually structured in some sense. And that's what I found in my research into magnetic resonance, that most water is structured. And what that means is these hydrogen bonds here restrict the water molecule from moving. And so the whole thing tends to move like this.
So when it's in a gas state, does the rotation change?
Yes, when it's in a gas state, the rotation changes. And so when the water has boiled, then you've got a different thing has actually occurred, that the hydrogen bonds have been broken completely, and then these molecules rotate independently. And also when it freezes, it locks completely into position. So the microwave isn't very good for melting ice. I hope that answers that question. So this forms, if you like, a sort of quasi-molecule, a massive molecule. That's called a phonon. A phonon is like a single particle that can now move like this. And so we're effectively moving and vibrating all of the water, and that transforms into random motions, which is heat. Now, the clue there is that the heat is the only method that people think that microwaves have for affecting biological systems. You don't necessarily only rotate, because the molecule can also vibrate. Do you see it can go like this? Yeah, and it can twist like this. And these bonds here, if they were flexible, would go in and out. So there are different modes of vibration. And so the particular frequency that affects water is actually quite broad. I can show you it here. So if I take water here, I can show this is the wavelength here, and this is the frequency. The frequency here is going up. This is 2.45 gigahertz, which is the frequency at which microwave ovens work. That's domestic microwave ovens. Commercial ones work at 900 megahertz. So they're at a range down here. And the reason for that is the wavelength is larger and those ovens are bigger. But our ovens are about the size of a wavelength or two. So they're a resonant cavity, and they sit here at the 2.45 gigahertz range. And this shows you how much energy is absorbed. We're looking at the blue lines here. Yeah? So the blue lines show us how much energy is absorbed at these frequencies. And you see that actually we need to come up to something like 9 or 10 gigahertz in order to get the maximum absorption of energy by the water. The microwave ovens sit at 2.45. Why? Well, there are two reasons for that. The first is that the Americans designed a microwave oven called the radar range. That's learnt from the fact that the radar heats up your tummy. And in 1944, when they were allocating the electromagnetic frequency spectrum, the American delegate specifically said, we have a manufacturer who has made a thing called a microwave oven that operates at 2.45 gigahertz, and so we request that 2.45 gigahertz be allocated as the frequency for microwave ovens. And so it was done. That's the way that standards bodies usually work. Someone has a special interest and demands that be respected, and so the whole world then ever afterwards is bound by that. Now, that range of 2.45 for microwave ovens is an unlicensed band. You don't need a license to use that band. And so everybody piled on as well. That's why Wi-Fi works in that band as well. Some cordless telephones and so on do as well. So everyone uses this band. It's also why your microwave oven may interfere with your Wi-Fi. But it's curious because it's not actually the band at which most of the heating occurs. Now, why might that be? Well, it's because these hydrogen bonds here are weakened if you have other things in the water. So if something gets in the way of the water, like salt, for example, then these are weakened and so are easier to move. And here, if you take beef, salt water, do you see here, the heating effect goes up at lower frequencies. So just compare those two graphs. This is pure water. So if you were designing a microwave oven to heat pure water, you would design it to work at about 10 gigahertz. If you're designing it to heat beef, you're perfectly okay to go at 2.45 gigahertz. And you can do an experiment if you put a glass of pure water and then a glass of salt water into the microwave. You will find that the salt water heats up more. So part of our problem is that the radiation is warming us up. And if I look at microwave radiation and I seek for a harmful effect, I first of all think about radiation. And radiation might mean X-rays, which are also part of the electromagnetic spectrum, or it could mean alpha rays, particle radiation. And those are what's called ionizing radiation. So ionizing radiation takes one of these perfectly harmless water molecules and actually knocks an electron completely off a part of it, or perhaps separates off this hydrogen, which now gives us a free hydrogen and a partially free oxygen. This is extraordinarily reactive because it is hungrily seeking out anything that it can react with. So ionizing radiation changes the nature specifically of water so that we have oxygen, and that's called a free radical. So we know that that does damage to you, but the energy of a microwave is not sufficient to break that bond. It's not actually sufficient even to break these hydrogen bonds. It can only bend them. Those break when the water boils. So microwave radiation finds it very difficult to actually vaporize water. You can get up to nearly 100 degrees, but not much more than that. Yeah. Okay. So what we end up with then is that the microwave radiation is considered to have heating as the only possible effect. It cannot cause a change in the molecular structure. However, it may do so because some people have detected effects of microwave cooking. This one, for example, is on cooking broccoli. If you heat up broccoli in a microwave oven and you heat it up properly, that is, you don't do it on too high a power and you don't do it for too long, it's found that some of the vitamins, some of the more complex molecules in the broccoli are broken down by the microwave radiation, but not by ordinary heat. And that is possibly because the specific rotation of the molecules, rather than just jiggering them about in general, is enough to change the shape of the water. So this structure of the water here gets modified. And that structure of the water also affects things like vitamins and proteins, because these things, the vitamins and proteins, fit into the gaps in the structure of the water and are shaped by it, and that's part of their effect. I want to show you something that's quite interesting to me, at least. And we'll just do a little experiment on what can affect microwave radiation. This is a Wi-Fi analyzer. I'm running it on a Kindle Fire, and you can get this on a phone. It's very easy to do. Just look up Wi-Fi analyzer and you'll find them. And this thing here that I'm using, well, this is all of the networks that extend into our house. I accept that a lot of them are mine because I'm kind of obsessive. But we'll forget that for now. This is a Wi-Fi hub. When I switch it on, it will create a Wi-Fi network that is actually called Sunscreen. Don't ask why. Sunscreen. It takes a little while to pop up here, and I think it will pop up here on channel 12. These are the different frequencies. So each network sits on a different frequency as it goes by. And eventually, this one should. There we go. Right. As I say, it takes a little while. I'll unplug that lead because that spoils the effect. So can you see here, this is the Sunscreen network. Yeah? Well, first of all, if I'm concerned about the microwave radiation reaching me, how could I screen myself from it? Well, I could put my hand in the way here. The delay is the latency in the Wi-Fi analyzer. Or it could be that I'm not going to see the effect I wanted. Ah, there we go. Do you see it goes down a little bit? So my hand successfully reduces the microwave radiation. That's because my hand does two things. First of all, my skin is very reflective of microwave radiation. About 3/4 of the radiation that hits my skin is reflected away from it. But reflection doesn't really protect me because the waves can swerve around my hand into it. But my hand also absorbs some of the radiation. So here, I'll do a little experiment with a piece of tin foil. So we all know the idea of the tin foil hat. And we'll see if tin foil stops the radiation. So this is partly the question that was asked about the holes in the microwave oven screen here. So if I put tin foil in front of it, we know that tin foil shields radiation. Now you'll just have to believe me because I'm not going to wait long enough. The problem with tin foil is that a Faraday cage, that is a shielding mechanism, has to completely surround the object. You have to totally wrap it up in the tin foil. So the idea of wearing a tin foil hat to protect your head from microwave radiation is unfortunately doomed because the hat has to completely surround you. You could possibly wear a complete tin foil suit, but even that wouldn't work very well because I think I can take this tin foil here and I can just wrap this whole thing completely up in tin foil, and there's still remaining radiation. So the idea that you can surround yourself with something that can completely cut out radiation is not actually supported by experiment or by theory. That's because the radiation acts as waves, and waves are reflected, but they're also bent by the things that are around us. By the way, if I turn on my microwave oven here, you might see, and you see some of the networks go down a little bit. That's because the microwave oven is not very close to me, but the microwave oven affects the networks also.
Are you on a Bluetooth headset?
Yes, I am.
Yeah, it affects Bluetooth as well.
Oh, does it? That's interesting. That's because that also poaches the same. That actually poaches the same frequency. So these things are quite useful because you can wander around your home and find the appropriate Wi-Fi hotspots and so on. But the thing to remember is that reflecting radiation is not sufficient. You need to absorb it. Skin is very good at reflecting and absorbing radiation, so it gives us an enormous protective effect. There's another thing that happens also, though, and that is that depending on the thickness of the foil, the effect is to make what's called an impedance match. An impedance match is something that matches a reflection to a non-reflection. And if I show you here, this is in fact looking at the thickness of clothing versus power transmission. So clothing tends to reflect a little bit of microwave radiation. And as you see here, this is the clothing thickness, and there's a resonant effect here. So it can increase the radiation that's going into your body or decrease the radiation that's going into your body, depending on its thickness. It's not at all a simple effect. I'm going to show you, if I can, the last little demonstration here. Somewhere I have a marble. Yes, I do. Now, I think this works. If I drop the marble in, it vibrates and causes waves. So I've made a little simple wave tank here. And you see the waves go out in nice perfect circles. So I get a nice perfect circular wave. But if I put the marble somewhere in the corner, you'll see that the waves go in a perfect circle, but they're also reflected a little bit from the sides. So that is, they're getting a reflection. Do you see here? I get the round wave, but then I get another wave goes out from here because it's being reflected. And if I put a barrier in the way, then the barrier refracts the waves. So if you look just behind this, can you see that the waves pass it by, but then curve in here? So that they across the barrier. And this is my tinfoil barrier here. And if perhaps it's better to do it this way around. If I create my wave, can you see that the wave turns around the barrier like that? So it's better to absorb the radiation than it is to reflect it or refract it, because that just bends it around where I am. Well, our body has different fluid compartments. So we have our blood and things like urine. Those are actually bulk water within us, and blood and interstitial fluids. Interstitial is in the spaces. But we also have water that's inside the cells in our body and water that's binding the cells in our body. And most of that is in close contact with surfaces. And we all know that water has surface tension. And so those effects change the way that water is affected by microwave radiation. The hydrogen bonding gives a structure to the water, and that structure can also shape important molecules in our bodies: proteins, vitamins, amino acids, complex molecules. In addition, water plays an important role in modifications of DNA, because water has these hydrogens attached, but hydrogens are very small, and water can quite easily lose one of these hydrogens and then sort of let it move. And that hydrogen can move along a DNA strand and then add on to cause a hydroxyl bond to shape or change the DNA. That's moderated by the shaping of the water, by the structure of the water itself and its protonization. So I see there are two methods by which microwave radiation might affect the human body other than just heating it up. One is affecting its ability to shape vitamins and proteins, and the other is the mobility of protons in changing our DNA. Well, if we look at these things, first of all, I'll digress a little bit, because I want to talk a little bit about the use of microwave radiation to look inside the human body. So that's to some extent how I came to know so much about what happens. Firstly, in magnetic resonance, we fire a very powerful radio wave, but it's not a microwave, into the human body. And then we apply a very powerful magnetic field, and we look at the rotation of the hydrogen nuclei. Microwaves are doing a different thing. They're looking at the rotation of the water molecules. This is my desk on the last job that I had. I was a consultant to a medical imaging company here, and this is a radar array. This is the machine that reads the radar signals, and then they're processed on the computer here. So this radar array is designed so that you can attach it to the human body. So the human body sort of sits up here, you lie. In this case, it's a breast scanner. So the woman lies with her breast hanging into the scanner here, and the radar array makes a radar image of inside of the breast. And this is the kind of image that we get. So here, what we're looking at is the normal breast tissue, and then we're looking for tumors. The idea is that tumors respond differently because they tend to be wetter or to have more blood in than the rest of the body. There are other more complex mechanisms for it here. So we can use microwaves to make images of the human body. In order to do that and to understand those images, we need to understand quite a lot about what water does in the human body and what microwaves do to that water. Oh, this is a picture of a wave that I had. It's out of order. So here the wind is blowing waves around this rock, and then they come and merge here, and you see the rock is completely surrounded by the waves, so it doesn't form an effective barrier. That's why your tinfoil hat doesn't form an effective barrier. One of the things to note about medical imaging using microwaves is that it's extremely difficult. Now, the reason for that is it's very, very hard to get microwaves into the human body. Why? Because the skin is like a mirror. So going from air into skin with microwaves is like hitting a mirrored surface. More than 3/4 of the microwaves are reflected away. So your skin is an excellent protection. Also, your skin is a very good absorber. So it absorbs the microwaves very rapidly. In the human body, the microwaves are slowed down by a factor of about 3. And in slowing down, their wavelength is compressed. So they go down from about 12 centimeters to about 4 centimeters. And half that is about the range they penetrate to. So they go into a range to a depth of about 2 centimeters. And around your body, your skin and the subcutaneous layers of it are about half a centimeter to a centimeter thick. So most of the effect of microwaves, whether it be heat or not, will in fact be on your skin.
We've just had a question come in. If the tin foil was made of lead instead of aluminium, would that make a difference?
No, I don't think it would, because it's to do with the conductivity rather than the weight of it. So we're not trying to block the radiation by a mass. It's not like blocking a gamma ray or a particle by actually stopping its passage. What we're trying to do is to create a barrier that completely surrounds the object. And the effect of the tinfoil is effectively to spread the electromagnetism across the whole sheet of tinfoil. So because it conducts, when the microwave hits the tinfoil, the entire sheet of tinfoil becomes electrically charged rather than this particular point on it. So it spreads out the charge all across. And unfortunately, when you get to the edges of it, it's not spreading anymore. But if you were completely surrounded, wrapped up in the tinfoil, then the charge goes all around you and effectively bypasses you and doesn't affect you inside. So no, that wouldn't have an effect. So here, what we have to do in order to get the signal into the human body is we use something called a matching medium. So that's what's called an impedance match. We have to have something that gradually moves us from the air's refractive index into the skin's refractive index, and that has to be extraordinarily carefully calculated and carefully prepared. So one of the things I would take home from this is that the effects of microwave radiation on the human body are probably lessened by the fact that our skin is much more reflective than perhaps people think, but also much more absorbing. However, you still have the idea that there may be some effects that are not thermal. So all of our health limits in the Western world are dictated by the statement that microwave radiation only causes heating. It's not an ionizing radiation. It can't cause free radicals, and so it warms you up. And so our limits in Europe are 2 watts per kilogram. So you can put 2 watts per kilogram of your body weight into you. And that's what a mobile phone does. So my Samsung X-Cover mobile phone puts about 1.4 watts per kilogram into my body. That's if I hold it about an inch away from my body. If I hold it closer, it puts a little bit more in, and that's slightly controversial. That 2 watts is less than is needed to cause a 1 degree increase in temperature anywhere in my body. And that 2 watts per kilogram is measured on a sort of spot basis. So it's not averaged over my whole body. It's just looking at where is the major heating. So it's the hottest point in my body is not to be elevated by more than 1 degree Celsius. And the rule for that is that we mustn't be more than 2 watts per kilogram. That's assuming that only thermal effects matter. But why are people worried about other things here? So here's an investigation into radiofrequency radiation in male and female rats. And this was performed by the National Toxicology Program in the United States. And they published this in 2018. It repeats some work that has been done earlier in places like Russia and China. What they did was they put rats in microwave ovens. Well, in resonant cavities, those are effectively microwave ovens. They did that because then the rats can move around. Previous studies had pinned the rats down. I mean, it doesn't bear thinking about what we do to animals in these experiments. They pinned the rats down in order that a radio antenna could be held against their head or against their heart or against their stomach. And so the rats in this case are living a much more normal life, but they're irradiated, and they're irradiated in 10-minute cycles, 10 minutes on, 10 minutes off, with 10 times the microwave radiation that's allowed to be put into a human body. Now, that's not a lot more. I mean, 100 times more is a lot more. 10 times more to a physicist is really sort of not significantly more than the radiation level that's allowed. And they tested these rats to see if their DNA was modified. And it's interesting. I won't go into these things in detail because I think here what comes out is not that the specific effects of microwave radiation, possible harmful effects of 5G, but it tells me something about the way we do science in the Western world, because we do evidence-based science and evidence-based medicine. And so in this case, this study is following that along by trying to find a specific damage. They're looking for damage to the DNA, and they found there is an element of damage in this case. That's to the hippocampus. There is some small amount. This is the dose in terms of watts per kilogram here. So the 1.5 is what a mobile phone would put into you, and 6 is 4 times that down here. Up here is nothing. So here you see that there's about 5.8 of these developed damage to the DNA. But under the radiation from the mobile phone, there was about 8, and then 8 at double the dose and about 10 at these doses. But these figures here, while they look worrying to start with, you need to interpret them in terms of the statistics. So not many rats were exposed, 40 in total. That's because you can only fit 5 into each resonant cavity. The test was done over 2 years.
Just a quick question from Marion. So if we have a mobile phone, a laptop and a tablet by us, is that really not a great idea? Please tell me it's not a problem, because I'm somewhat surrounded at the moment.
I never thought about that. It's probably not as good as it should be, but the mobile phone is actually held to your head or held to your body. The worry at the moment is that the limits for mobile phones were set in the 1980s and 90s, and people like me carry their mobile phone on their belt, which means it's about half an inch away or an inch away from your body. But now people stuff them into their back pocket, so you're literally radiating your ass from close up, and no one's done a study yet on the effect of mobile phones on your buttocks. But people are holding their mobile phones much closer to their bodies now, and that's where the concern arises. So your laptops, your microwave oven, and so on, they're far enough away from you that the effect isn't probably worth worrying about. But these figures here, these are very confusing because they're called the p-values. Well, some people confuse them with probability, but they're to do with what's called significance, and they measure the possibility that these results could be just due to random variation in the population of rats. So here we say that 5.8.
We've had another one which seems to be a valid concern, and is putting your phone in your trouser pocket a bad idea?
I would think it probably is, yes, because there are some studies which have been done. The measurements that the manufacturers make. And you can look up your phone. You can go online and look up. It's called DSAR, the specific absorption of your phone, and it tells you the amount of power that's dumped into your body at maximum by that mobile phone. But that mobile phone is held 5 centimeters away from your body. So specifically, it's designed that you're not holding it flat against your ear, you're not holding it close to your heart, you're not actually sitting on it. If you put your mobile phone closer, there's quite a lot of evidence that the exposure goes up by a factor of 2 at least, and that then exceeds the limits allowed. Now, this was pointed out to the mobile phone manufacturers, but their argument, quite correctly, is that the standard requires them to measure at a 5 centimeter distance. But that might be out of date in terms of how people are now using their mobile phones. So I would say it isn't a good idea, but the organs in your body that are most affected by thermal effects, by heating effects, are your eyes, first of all. So if you heat your eyes up too much, they become like a poached egg, so they go white and opaque. So that's not a good idea. Don't microwave your eyes or hold your mobile phone up to your eyes. Also, your testicles. So don't hold your mobile phone near your testicles, but the damage to your testicles is temporary. It kills your sperm and therefore renders you temporarily infertile. But so long as you're a fit, healthy man, you'll produce more sperm later on. So it's basically don't hold it near your balls or near your eyes, because both of those are particularly sensitive regions. So I think having it in your back pocket is probably safe, because I can't think of anything that's crucial that's actually in your buttocks, particularly if you're a very large sort of person. So perhaps you can get away with it like that. Anyway, back to my p numbers here. The p-values are widely misunderstood. And that's because they're actually extraordinarily confusing, and they require an analysis of the distribution of the individuals in your sample population. So they're trying to say, really, in this case, we tested these rats. We had one population that weren't exposed to radiation, then we had another population that were. We saw that more of the population that were exposed to radiation developed damage to their DNA. Could that result just have been a statistical variation in the populations of rats? If I'd taken a different 20 rats, might I just have seen that? Yes. And this number here tells me how likely that is. The smaller this number is, the more likely it is that my result is just random chance. And so up here, this one is important because this 0.135 here, that is significant. That means that there's more than a 1 in 20, there's less than a 1 in 20 chance that this result was produced by random chance. However, if I look at these, there's an awful lot of measurements done. They tested male rats and female rats. They exposed rats to radiation while they were a fetus in the womb. They exposed different varieties of rats. They did 25 different combinations of tests on this, and only one of these showed a result. So that, in a sense, might be called hunting in the data. You're doing so many tests that some of them are bound to throw up possibly a false positive, but it is something to be concerned about. There were some what they call equivocal results as well. There are equivocal results where the result is almost significant, but not quite. Yeah. And in each of those cases, they were affecting nerve cells. And the DNA test is a proxy. That means it's a quick way of testing something that might lead to the development of a tumor. They didn't test for the development of a tumor. They tested for potential damage to DNA that might lead to a tumor in this case. One of the things I want to go into, because the 5G, are we stopping for the clap for the NHS or?
I think it would probably be a good time to stop for 5 minutes, let everyone grab a drink, stretch their legs, and then come back for wrap up and any questions.
If you give me if you give me 5 minutes pause for the NHS, and then I'll come back and wrap up afterwards. Is that okay?
Yep, works for me. So everyone will be back in 5 minutes. And for anyone who's enjoying this and still here, we've got about 2 minutes before 8, so I'll be heading out for the clap then. But this is the next one we've got coming up. If you want to look at alternatives, if the whole mobile radiation thing is putting you off this planet, we've got Professor Ken Rice talking about other planets, and that will be next week. So for those who are back, we'll just give it another 2 minutes and then kick off again. And we'll start off with a couple of questions for you, Chris.
That's fine. Look forward to it.
Are you ready? Are you there? James is just talking to you.
Yeah. Yeah, I am here. Yeah.
You need to keep aware of which way is the right way up in case you put things sideways.
From experience, because we did hear that, I highly recommend when you're working in that sort of way using a camera, putting an arrow on the thing you're working with.
Yes,
I've had to do that before because it can get very confusing.
it certainly does. All those experiments you can do at home, of course. The Wi-Fi analyzer is really interesting. Get your children to do it if you have children. They can go around the house and map out all the Wi-Fi hotspots for you.
Okay, so first question that we've had written in is, you mentioned at the start of your talk that electromagnetic waves propagate through thin air. How can a wave propagate through nothing? And I think you actually said empty space rather than thin air.
Yes, I did. It's a really weird thing, isn't it? Yes, I mean, we used to think, well, people used to think it was what's called the luminiferous ether because the wave propagated through the ether. Then people started talking about photons being a particle. So the particle can obviously be thrown through empty space, but I don't think that's particularly convincing either. The reality is that it's quite a mystery. And I think a lot of these things are. Maxwell's equations describe what happens, and they describe a way in which magnetism can create electricity, and that electricity in turn creates magnetism, and that magnetism in turn creates electricity. But how the devil that actually works, I don't think I know at all. The quantum mechanical model of it is much easier to understand because you think of the microwave radiation as a photon, a particle, a sort of blob flying through space. There's a huge problem with that, though, for me at least. And it's possibly a limitation in the way I think, because I tend to over-concretize everything. I'm not brilliant with abstractions. I tend to think, oh, but how big is that? And how could that work? So a microwave is around about 10 to 15 centimeters long. So it's about this big. The size of a photon is not much more than its wavelength. It's not smaller than its wavelength, certainly. So a photon of microwave is going to be about this big, and it interacts with a water molecule that is 1/10,000 millionth of a meter across. Now, how does something this big fly in and hit something that small? I can do that by any number of classical models and say, well, it's a wave and it vibrates the water molecules. But as soon as I step into that quantum realm, which is actually where I actually do study it, there's a conceptual step that I think is extraordinarily difficult to make, and that's probably why quantum electrodynamics remains a cutting edge field of research in terms of trying to figure out what on earth we really mean. You can talk about it as a probability wave. So the probability wave replaces the microwave with Schrödinger's wave equation for the microwave, but that doesn't really help because the probability wave is still actually remarkably big. I mean, interestingly, radio photons are even bigger than that, and they could be a mile long. So a mile long quantum leap is actually quite a big quantum leap to contemplate. And radio 4, interestingly, is about twice the length of a human being. And that actually means that the human being acts as a very good aerial, because when you're about half or a quarter of the wavelength of the radiation, that means you're resonant. And so the radiation that you absorb, best of all, is actually, in terms of being a human aerial, is actually radio 4. Which means that radio 4 is probably one of the hardest stations to tune in to to an FM radio, because you're actually acting as an aerial and getting in the way with it. You should tune your radio by remote control from another room. I don't think I have an answer to it. I mean, this is why I think it's so fascinating. The whole, I can do the quantum mechanical formulation, I can do the classical electrodynamic formulation. The equations are fine, they speak to me perfectly all right. But the concrete, genuine interpretation, how can I have a quantum that big that interacts with something that small? That really leaves me gasping for breath, as it were. Maybe there are people cleverer than me who know how to do that. We had a question there about oh, sorry, go on.
Yeah, I was going to say there's a couple more.
Yes.
For several years, I've been a subject in an experiment on the effect of non-ionizing radiation running from Imperial College. Do you know anything about this?
No, I don't know that one. I mean, I know a number of people who've experimented with non-ionizing radiation, but I'd be very interested to hear about that. I mean, if that person has something to add, maybe you could bring them in on the conversation, or we can talk to them later.
I've not disclosed the name just in case it is medical related or similar, so I don't want to give anything away. But if you'd be happy to talk afterwards when we've got through a few more questions, and I can promote you to speak directly to Chris, if you'd be happy to do that, then please just drop a message in the chat and I'll arrange it. And we'll just cover
There's some very interesting things went on. I mean, when I was involved with the Royal Navy, only very peripherally, I was what was called a guest lecturer at the Royal Naval Engineering College. But there were people there who were very interested in subsea communications, extremely low frequencies. And one bloke became obsessed. Well, no, he was interested. He was interested in the idea that you could detect electromagnetic radiation, and particularly at extremely low frequencies. So he equipped his basement. He made it into a sealed Faraday cage, and then he put cables all around the walls. I think he was a lieutenant commander. And he then would sit there and have it randomly generate extremely low frequency waveforms and see if he could detect them or not. He was convinced he could. And a lot of research later on has shown that actually, at least low frequency radiation, human beings are actually quite good at spotting when it's on or off. I don't know what the mechanisms are for that, but it's interesting.
Right. I'm just going to suggest we answer what I think is the quick question, and then I'll bring Avril onto the panel to talk to you directly. So
okay, can I before I do that, or after that quick question, I've got two more things I want to say to complete the talk.
Okay, so what is the shortest and longest possible wavelength of an electromagnetic wave?
Oh, right. I don't think there's any practical limit to it, in actual fact. I mean, it's microscopically small and infinitely long. There is no end to the electromagnetic spectrum, either theoretically or practically. There should be, because there should be a smallest quantum below which you can't go, but I don't know what that would actually be. Okay,
if you wanted to just do the wrap up then, and then I'll set up the additional panel.
I mean, when I'm talking about things like microwaves, and because I was talking about microwaves here, and we've had the 5G conspiracy theories and the mobile phone masts being dismantled and burnt down and so on, it's clear that there's a lot of concern from people about how microwaves affect human beings. And my attitude to all of that is that I think quite often science responds incorrectly, or at least in a not productive way, and that is to dismiss it. So when I was preparing for this talk, I of course reviewed that literature and the responses to it, and it's all too often the case that people say, oh, it's ridiculous, it's ludicrous, it's stupid, it's a conspiracy theory. And of course it may well be, some of it may well be mischievous, but I choose to believe that most people are not stupid, and mainly are not necessarily misguided or mischievous. And so it's better to try to engage with what the mechanisms might be. Now, I can see that those mechanisms, to my mind, are not supported, and the evidence suggests that when people say those things occur, they probably cannot duplicate that. But we live in a world of evidence-based science and evidence-based medicine, and coronavirus is showing this quite well, that we have evidence-based science, but then all of us scientists disagree on what the evidence actually shows. And that's perfectly reasonable because it's the way that science actually occurs. But we've maybe promoted evidence-based into a sort of denial thing where we can say, oh, there's no evidence for that, end of. The real response should be, let's discuss it, let's seek for the evidence for that, let's see how it might work. Let's not necessarily panic straight away, but let's at least investigate it. But here's something quite interesting then. This begins with Russia. In 1944, microwave ovens were invented, and I believe that they were first deployed by the Nazis in the invasion of Russia, because they were a convenient and quick way of cooking food for the troops as they pursued the invasion. Actually, it was a bit before 1944. 1944 was when the ovens were readily established. And so microwave ovens in the Soviet consciousness became associated with Nazi technology. The question to my mind is, how the devil did the Nazis have really good electricity supplies everywhere so they could use microwave ovens while they were advancing? But that's a different issue. From 1953 to 1976, microwave ovens were banned in Russia. You were not allowed to have a microwave oven because of the harmful effects outweighed the benefits. That's interesting. So that's an entire nation. Nobody's entirely sure why, but the anecdotal evidence suggests that they detected physiological effects from microwave ovens and therefore were highly suspicious of them. In 1976, Gorbachev went through perestroika, the opening up of Russia to the West, and that involved an acceptance of Western standards. And so microwave ovens became permitted from 1976. Not evidently through a review of the scientific evidence in Russia, but more from just accepting American standards. That's quite intriguing. Second thing that happened in Russia is this, that over about the same period, the United States Embassy in Moscow was subjected to mysterious microwave radiation. Now, in those days, microwave radiation was a peculiar thing because it wasn't just everywhere. There was a 2.45 gigahertz radio signal that radiated the US Embassy in Russia. They assumed that other embassies were not so irradiated, and a study was done of the effects on the personnel. There were about 4,638 staff members who had worked at the United States Embassy in Moscow during that time. And around about 1973, the radiation increased by a factor of about 10, so it became extremely noticeable. And the study concluded that there were no harmful effects. The study was done by Johns Hopkins University, and it compared the staff who'd worked at the Moscow embassy with staff who'd worked at other embassies, United States embassies. And one of the criticisms was, well, how do we know that they weren't irradiating all those other embassies with microwaves and we just didn't detect them? The study became available publicly not all that long ago, and it's quite interesting because I think it shows the difficulty in these kind of things. So actually, what was found was this. They looked at the mortality rates of the people who had worked in the Moscow embassy, and they correlated them with things like their gender, their age, their employment history, other things, and whether they'd been sitting near a window while they worked there. And it's a very diligent study with quite a large number of people. Curiously, they found that the people in the Moscow embassy lived quite a bit longer than people in other embassies. Now, I don't think that necessarily shows that microwaves are good for you, but the study I showed you on rats, and the rats developed damage in their DNA, the rats that developed damage in their DNA, curiously, lived significantly longer than the rats that didn't develop the damage in their DNA. Maybe because they were a little bit warmer. I don't know. Nobody knows exactly what it is, but there are some very peculiar things that go on. The review of that Moscow study actually suggested that there weren't mistakes in it, that actually it showed that there were no identifiable long-term harmful effects. But this, if you can read it, is the exposure limits in different nations. So here we have the watts per square meter. So that's different from the specific absorption rate. That's how many watts can hit you on your body here. Watts per square meter. United States, 10. Other nations, including United Kingdom, 10. China, 0.1. No, that's 10, 0.1. That's 100 times different. Russia, 0.1. Switzerland, 0.1. Now, the typical exposure you get from a base station, so if you're standing, and you can see the base station very easily, so you're about 50 meters away from it, something, is 0.01. So it's 1/10, but the handset is easily 100 times or 1,000 times that. Why do those other nations have such radically different exposure limits? It's not particularly obvious why, but the Russians specifically say that those limits are based on experiments with animals that showed a physiological effect, but they can't point to what those experiments were or the published papers that evidence them. The Russians also indicate that they were looking at reported effects from people, and those included headaches and nausea, ringing in the ears, fatigue. Those things are the kind of symptoms that people say they get from living near mobile phone masts or using their mobile phones excessively and so on here. But in our world of evidence-based medicine, we don't accept that because it's not falsifiable. So there's a definite difference in terms of what people accept as evidence-based. The interesting thing here is that this one here, which is the United States, an exposure limit of 10 watts per square meter, is science-based. This one in China, which is 100 times smaller, is science-based. I would respectively suggest that we have a problem with science when this occurs, and that we urgently need to look at least harmonization. Now, I'm not suggesting that things are worrying, but I am suggesting that we need to spend more time looking at these odd effects and the peculiarities of these particular things. Science is not quite as clear-cut. It's complicated, which is why we love it. But when it really matters, maybe we need to drill down a little bit into the complication. Thank you for listening to me. I've enjoyed talking to you.
Okay, well, they're going to listen a bit more because I'm just about to bring Avril into the panel, if I can. And she should be rejoining shortly. There we go.
Hello, Avril. Now we need to unmute the microphone.
Just muted it. Hi there.
Hello, Avril.
Yes, I'm a subject and an ongoing experiment. There's not an awful lot I can tell you about it. I wondered if you'd come across anything in your researches.
No, I hadn't, because I didn't know that Imperial were doing that kind of investigation. Could you're a subject in the experiment?
I'm the subject. Oh, excuse me. Yes.
Yeah, interesting. And that's into
yes, I do. I'll be down shortly. Sorry.
Yeah.
Yes. I've been a subject probably for in the region of 10 or 15 years now. It's quite a long time. And I was asked to become a subject, apparently chosen randomly throughout the population. There's a large cohort taking part in this. And we were asked to allow access to our mobile phone records. We were asked to allow access to our health records. And we are reviewed every so often. And I was last reviewed, I think it was around about Christmas time, not very long ago.
Yeah.
And you were asked quite a lot of questions about, how your life has changed, about your mobile phone use, about what ear you hold the phone to, how long you use it, although you would think they could find that from the records. They've now added induction hobs to that.
Oh, really?
And we just got an induction hob, so I'm now thinking I need to stand a long way away when I'm cooking. And there was a little bit of preliminary reporting recently, but it seemed very much to do with how the experiment was set up and things like that, rather than actual outcomes. So
Yeah,
I'm waiting to hear what happens.
that's fascinating. Yeah, it's the kind of work that really needs to be done, because it's a very complex subject, and you need to look at all of the kind of behaviour. The problem with mobile phones, of course, is, as with other new technologies, that not only have they not been around for an entire generation, but their usage has changed so much. So you're actually trying hard to do science in a field that's constantly changing. And I think that makes it difficult, hence the recording of what you're doing. And then you end up with a multi-parametric mess that's very difficult to disentangle. But it can give you some ideas as to what is actually going on.
On that constant changing.
Changes, and also if you're self-reporting, it's fairly inaccurate, I would say. They have to look at the actual data.
Yes, you get a sample bias from people, choosing what they say or not. I remember a marketing director of a company I worked for when I was very young pointing out to me that if you asked, I suppose in those days it was sexist, he said, if you ask housewives how often they clean the toilet, you would think that you would sell more toilet cleaner than you do. And I think there are problems, but we have to work with these things. We've got to adopt these much more subtle and nuanced measurement. I think the coronavirus shows us a brilliant example of that the scientists on their own are isolated. When they come out into the spotlight and start interacting in public, then the science actually develops, and it's informed by what members of the public think about it, and also by their input into it. So it can't really be done in ivory towers anymore. James, you're trying to interrupt.
Sorry.
Yeah, no, it's fine. I was just going to interrupt and say that on the subject of science or technology constantly changing, for anyone who'd like to see something about that, last week's talk by Dr. Orban covers almost exactly that. So
yes.
It's very relevant if you want to look into that part of things.
Yes, we're scared of everything until we get bored of it, and then we get scared of something new. And I think there is that, and it's something we have to guard against. The other thing that I think is interesting is that my mother knows someone who she worked with. She used to be a scientist at the NPL until she got married, and then she had to leave because you couldn't work at the NPL as a married scientist. But that was a long time back. But she knew a scientist who worked there for quite a long time. And his daughter committed suicide. He became convinced that it was because of the effects of a mobile phone mast, which was very nearby, extraordinarily close to where she had been. And that's not someone whose view I'm prepared to entirely reject, but I can see that it's a very rare occurrence. And I think one of the unacknowledged things is that if a condition is extraordinarily rare, then it may not be possible to duplicate it, and that rare condition therefore may be excluded from consideration. So what they call athermic effects of microwaves, that is, maybe it does something to you that's not just heating you up or cooking you.
Yes.
If those do exist but they're extraordinarily rare, then the way we work, we don't actually care about them, because our science says, unless you can show me this in statistical numbers, I'm not going to accept it. No.
Yes, and you're dealing with bell curves and things like that, and people at the end of the curve.
Exactly, that's right. I don't know what the answer to that is.
These effects are talking about the protons affecting the DNA structure. And the hydroxyl atoms. This is ion compounds. These sound like epigenetic effects, and they could be things that have different effects according to where in the genome it has occurred.
Yes, exactly. And we take an assessment of risk. I happily use my mobile phone and carry it with me all the time. So clearly I'm, confident with it. But when I go outside with the COVID, I try to keep 2 meters away from people. So I've got an assessment of risk in all of these things that I make myself. But I hope that I'm well informed by others, and I think I get very concerned when I see things being just dismissed out of hand by scientists who know. And I think the better approach is to take something seriously and then to express a view that that's not a significant risk as far as we know. Therefore, but
in your figure of 50 meters away and 0.01 watts per square meter exposure. But 50 metres is a long way. And if you're putting
Yes.
masts on houses, you might be 10 metres away if you lived in the top floor of a block of flats, for example.
Yeah, it's exactly right. I mean, curiously, 5G we're better with than 4G, because 4G is a longer wavelength, therefore it penetrates more into your body. So the 5G, actually, the reason we have to have more masts is that it doesn't go so far, and it will probably only go about 1 millimeter into the skin anyway. So the effects are likely to be more like sunburn. I mean, it's not enough to cause sunburn, but they're very peripheral effects, and it can't get into your house. But those are things that one has to make people aware of, and it's quite a complex conversation. I think you need more masts so you don't have more power. I mean, the other thing is if you live close to a mobile phone mast and you use your mobile phone at home, then your mobile phone uses less power. So the power limit for the mobile phone is the maximum it can generate. If it's close to a mobile phone mast, it switches itself down in power to economize its battery, and therefore it exposes you less. So if you're using your mobile phone close to a mobile phone mast, you're exposing yourself less to the radiation from your own mobile phone.
So now, would you be happy to have a mast on top of your house, for example? Because this is actually an issue we've got at the moment here.
Yes. Yeah. I mean, Winston Churchill School in our town has a forest of mobile phone masts on the roof, and obviously that's a concern. But the masts are designed. Nobody designs a mast so that it blasts radiation directly into the ground, because that's not economical. What they do is they design the masts so that they send out a disk of radiation. And we're very good at doing that. So we know for sure that it's called the antenna factor, that the antenna is not radiating downwards very much. So actually living under a mast is probably the best place you can be, because they don't want you to get good reception. I've never tested it, whether the reception is worst right underneath it, but theoretically it should be, and that would be an interesting experiment.
From experience, I can vouch for the fact it is, because for the company I worked for, visiting one of their masts or one of their switching centres with a mast, the reception was horrible until you'd got about 20-30 metres away from the building.
Oh, well, there you are. They had really good beamforming design then. Yeah. And the other thing with mobile phone masts is they do direct the radiation at you if they can. So does your Wi-Fi router. So they do a thing called beamforming, which is to focus the beam. So if I'm using a device that's using Wi-Fi, my router will try to focus the beam so it's more intense towards me. But it can only do that for about 4 or 5 devices, and there are so many devices in this house that it's totally confused. But the masts do that as well. So these things are actually quite complex. We've got some very, very clever processing that goes on, and it changes everything really. But yes, I wouldn't be so worried about a mast being on top of me, but one being beside me, I might be a little concerned about. I think. But I don't know when I was doing MRI, we had the statement that was made was there are no known permanent harmful side effects. All of those things were said because we were very careful about it. And the record of MRI shows that it seems to be an extraordinarily safe technology, but I never thought it was. I mean, I went in an experimental scanner once and vowed never to do so again because it's the most stupid thing I'd ever done. But because you were using PhD students as guinea pigs without any kind of ethics committee approval whatsoever. But experience has shown me that MRI must be safe, otherwise we'd know about it. And I could never see a reason why it wouldn't be safe, other than the fact you're exposing people to massive magnetic fields and kilowatts of radio frequency. It's vastly more than the power that comes of a mobile phone. It's like 1,000 times more, but in short bursts and for a medical purpose. So it's
But people who live up on top of mountains are exposed to radiation from the sky. Are they not supposed to have greater longevity?
Yes.
Thinking about your talk about the rats.
Yeah, that's right. Some people it does seem extraordinary. And it always seemed to be men as well, unfortunately. And the male rats got damaged to their DNA, but the female rats didn't at all. And it's better to be. So it's probably why women live longer, and there's a reason for it. It might be there's more health there.
Yes.
But that study sounds fascinating because I wasn't aware of that, and it's exactly the kind of study that is ongoing and we need to have, because we must look into these things carefully. It's interesting that the Swiss limit. So Switzerland follows China and Russia in having a very low limit, but Switzerland does it for a different reason. So the Chinese and Russian are science-based, but they're based on Russian and Chinese science that the West doesn't accept as science. But the Swiss limit is based on a precautionary principle, and they based it on what is technically and economically feasible. So it's the lowest exposure that is technically and economically feasible, rather than something that's proven to be safe. So they accepted that there's no evidence of a harmful effect, but even so have said they're going to do this. But Switzerland had a massive campaign against mobile phone masts from their public, so that may be a political decision, but it seems a reasonable one. Make it as little as possible, do as little harm as possible and keep it cheap. That seems perfectly okay, really.
Would that not be a good policy for us to adopt then?
Yes, might be.
Yeah.
Okay. Thank you. I think you had one other question or thing to mention, Avril, about the scales.
Oh, this is such a silly thing. I'm almost embarrassed to ask you, but I'm aware that the microwave oven is generating radiation. But what amazes me is that my electric scales, which are battery operated, won't work properly because the weight just goes up and down as you watch it. It's interfering with its weighing, and I don't know
with the
why.
microwave.
It's interfering with the operation of the batteries inside the machine.
Oh, that's interesting. I mean, the scales measure your BMI or fat percentage as well as your weight.
No, this is for cooking.
Oh, for cooking. I've no idea.
I'm weighing out my butter and my flour. I'm about to make scones so I can eat them on VE day. Turn on the microwave and immediately it goes haywire.
Well, I mean, I don't know why that would be, but it sounds like the microwave's not well designed.
I can see two possibilities. It might be the microwave's interfering, or you need to get it to a research lab because you've developed anti-gravity. Right, with that, I'm going to jump on to the other questions. Avril, I'm just going to put you back into the attendees, if that's okay. So let me just do that. And yeah, we did just have a few more questions. So Gavin, and I think this was about the Nazis with their microwave meals, asked about DC batteries as the way to provide a reliable electric supply.
I guess it could be, yes. I don't know what the mechanism was. I mean, presumably that would be an ideal way of doing that. You'd then have to step it up to generate the microwaves, but they're fairly powerful things. It's quite interesting how much stuff comes out of wartime in those cases.
And Marion, I can't think why she's asking this. It makes me wonder if the offspring of those with damaged DNA show any differences, or the rate of success for trying for offspring.
There's no way from the National Toxicology Program study. It's very frustrating because what they did was they measured damage to DNA, which was a proxy for getting cancer. But actually, they didn't measure the damage to DNA. They did something what's called a comet assay. And a comet assay is you treat the DNA in such a way that it all curls up into a ball. If it curls up into a ball, you assume that it's not damaged because it's properly curling up. If it has a little tail to it, so it makes a ball, and if that ball has a little tail to it, then that tail is what they measure, and they assume that that's damaged DNA. It's not obvious that it is, but it's a standard way of doing that test. They don't do anything like assess whether the DNA is genuinely damaged. They didn't do anything to detect whether there were actually tumours in the rats, and they did nothing to look at their offspring or the success rate of trying for offspring. Plus, they invent a new term, because when it's like this, if the comet assay goes like that, they called it a hedgehog. And then they said the hedgehog had a tail. I mean, I don't know what they were playing at. They must have been on something, because they were inventing new terms all over the place. But no, there's no evidence of the rate of success of trying for offspring, but microwaves definitely can damage sperm. And so, but that's a temporary thing. It's not a permanent. not a permanent thing. And the damaged DNA was in the hippocampus, so that wouldn't affect that either.
Okay. And the other question we've had so far, there might be some more coming in a bit.
Yeah.
Does this mean Chinese handsets are less powerful?
No, it doesn't. That's really fascinating, isn't it? Nor are Russian handsets. They have Samsung and Apple iPhones and so on. Those all meet Western limits. So the Russian and Chinese limits must not be respected because the handsets they use are definitely of the same power levels as ours. That would mean that their regulation is stricter, but their enforcement of the regulation is lax.
Okay, there's a couple more that we've had come up in the chat, and I'm going to do some interpretation on one of them. One is, how about holding your phone? Is this not a good idea either?
Yeah, you mean it affects your actual your hand. I can't see that the hand is not known as a particularly susceptible to damage organ for being warm. I mean, you're always holding warm things and warming your hands up, and so it's not I can't see that that would be a particular problem of holding it in your hand. I mean, the worst thing would be to stick your mobile phone on your head. I would guess that's probably the worst thing you could do. Or, I mean, there are people watching in the next room and they've all got their laptops on their laps. So that's kind of bad news for those of them who've got testicles.
Okay, and
there are
there's
things you could do.
There's a couple more which I'm going to be delicate with. One is, does 5G work on microwave levels? I'm assuming that's talking about the microwave frequencies.
Yes, it does. So 3G and 4G go up to about 5 gigahertz, something like that. I mean, your Wi-Fi signal is 2.45, that's the microwave, or 5 gigahertz. So those are the two that are used for that. 5G ranges over a whole range of frequencies. So I think it goes up to 60 gigahertz, but it can come down to 900 megahertz. So the earliest mobile phones were 900 megahertz. That's a little bit less than 1 gigahertz. 5G goes up to 60, but it steps itself down. So it's a very clever service. If you're far away from the mast, it realizes it can't reach you with the 60 gigahertz. So it steps it down to give you a longer wavelength. So it uses the entire range. It sort of sucks up everything that there is and uses it as best it possibly can. It's a very, very broadband, very, very intelligent, clever system.
Okay, and the other one, and I am going to interpret this, so I do apologise if I've got it wrong. I've heard that 5G will mean that oxygen levels are being used. Is that right? I assume that's talking about oxygen emission wavelengths or oxygen absorption wavelengths, one of those two. If that's wrong, then please elaborate in the chat, or I can bring you onto the panel, but hopefully I'm close.
I think that my feeling is that that's not quite right. That there are a lot of statements made about 5G that it affects things. The microwave radiation is really affected mostly by water, and it's scattered by dust. So dust tends to scatter it in all directions, but it doesn't absorb it. But mostly water has the peculiar property of being affected by microwave radiations. Molecules like oxygen, they don't have the hydrogen bonds, and so they move incredibly more freely than water can. That's why they're a gas. And so I've not seen any evidence, but I have seen that 5G it has been said to be implicated in things. I mean, obviously there's the statement of it spreading or helping to spread coronavirus, that it changes oxygen levels and things like that. But I've never seen any evidence whatsoever that has actually been studied in any meaningful way whatsoever. That doesn't mean it's not necessarily so, but it's not a mechanism I could even imagine could interact.
And apparently I was close enough to the question, so that covers that one. We've also had a couple more. One is, what about ovaries? Because obviously you've mentioned microwaving your testicles is a bad idea, particularly if they're still attached.
Yeah, that's interesting. I mean, here we hit straight into something that I hope Cafe Sci is going to deal with in the near future, and that is the inevitable bias of science towards white male middle class individuals. It's not common to have tested on females. The rat study was interesting because it tested on female rats, but it didn't test for particular organs. The ovaries are the human eggs are larger and more robust than sperm, and so it would seem intuitively that it's an unlikely mechanism, but I'm not aware of a particular study on that.
Okay, and another interesting one, this one from Gavin. Should we actually be calling 5G broadband?
Yeah, you could do, because it's incredibly broadband. Well, each channel is not broadband. It's more like, you know, the actress Hetty Lamar, who designed mobile phones when she was doing sonar. She was a wartime actress, and she's used in many image processing examples. I think she's there looking sideways with a hat on and so on. But she was an actress, and with her husband, they developed this idea of frequency hopping for sonar. So you could be undetectable by constantly changing your frequency band so that people couldn't tell you. You know, you pop up on this band and suddenly you're swapped to another band, and that's the CDMA, which is the American system of codebook division, multiple access, and frequency hopping is a way of hiding your signal, but it's also used in mobile phones. If you use the Wi-Fi analyzer, for instance, and you have a clever router, what you should see is that sometimes your Wi-Fi will hop channels, so it will come on like channel 5, and then it will find that it's busy because all your neighbors are also on channel 5, so it'll suddenly hop to channel 12. And so 5G does more like that. It hops the bands rather than using all of them, so it will switch you between bands. So I'm not sure what the term for it is. It used to be called frequency hopping.
It's still frequency hopping. I've got a book on
Oh,
intercepting
right.
and hacking it, and it's still frequency hopping.
Yes.
Right, that's all of the questions we've got at the moment. So
thank you.
If you stick around for a few minutes, I'll just talk about what the next one's going to be. And if anyone does have any more questions, now's the time to ask. The next Cafe Sci we will be having, let me just change the video. Right, sorry, you've got me again. The next one we will be having is talking about exoplanets, so planets in other solar systems, as well as the climate of our own planet. And this is with Professor Ken Rice, there we go, who has done a lot of work on this, and you can get all of the details of that on our website, on our Facebook page, on Twitter. Take your pick, but the website is the easiest one because everything's in one place, and the website link is there. It should be easy to remember. That will be next Thursday at 7 o'clock, and then we've got a full schedule for the rest of the month, and we've started booking up June as well, so it's going to be quite busy. We will also hopefully be announcing a special edition Cafe Sci, which will be out of the normal schedule and with a panel later in the month, but I'm just working out the details for that with the panelists and the chair. If you know anyone who would like to speak or has something interesting to say and wouldn't like to speak, but you could talk them into it, one of these, then please put them in touch. If you have any questions about it, again, get in touch. And no other questions have come in, and we've gone for nearly 2 hours, so I know that I could do with a stand up to stretch my legs and get off this chair, and I'm sure Chris and all of the rest of you could as well. We would normally do a round of applause for the speaker and suggest that attendees contribute to a glass of wine. We can't do that at the moment. So Chris, your next glass of wine is on the audience, obviously. If we could get applause from people, you can either click the button, send applause in spirit, however you want to do it. Hopefully you've enjoyed this. Feedback is appreciated, and we will see you soon. And I'll shut this down in